Okay, I'm starting. So today we are going to start our study little bit. In last two classes or in last week we have learned something what we will be learning. But today we are going to learn something about the UV spectroscopy. Actually, what is UV spectroscopy? This is a kind of spectroscopic technique. Then what is spectroscopy? Spectroscopy is something, the interaction of light with some matter. I have a like this. This is a visible color or visible light, and if we have some interaction with the material and giving the light to my hands, so some of the light is reflecting and some of the light is absorbing. You cannot see any light going through my hands because this is very rigid, or you can say this is too dark, or it absorbs all the lights, most of the lights, because otherwise if it would not reflect at all, in that case you should not see anything. But as it reflects something, you can see some light. Okay, so we will learn the spectroscopy, that means the interaction of light with some matter. What happens and what are the applications of UV spectroscopy? So, why is it working? Okay, here you can see the basic idea of a spectroscopy. That means this is an instrument. Actually, we use these types of instrument. Inside, we have several things. We have some cells and some source of light, some detector. We will discuss everything in detail. So, this is some photos you can see. But what does it mean? Ultraviolet spectroscopy or ultraviolet visible, UV visible, UV, and then visible. So we will use these two lights. Normally we can see only the visible region. That means what we see in last class I have mentioned around 450, but actually we can see little bit large, 390 to 780, something like this. If we exactly mention, maybe in my next slide you will see somewhere what is the exact range. Anyway, just that is around what I have mentioned, 450 to 800, like this. But visible only this range, and UV, the wavelength which are smaller or shorter than this. So in case of energy, we will consider that the energy for this light is higher compared to this visible. And in last class, I have mentioned one thing. Why do we use sunglasses? Can you remember? Or I didn't tell you? Okay. Then I will tell you why we use sunglasses. That is very interesting. Because when we will see the energy of the lights, if I use this light, even if I don't want to put this light towards my eyes, but if accidentally, if this light go inside my eye in that way, now my eye is closed. But however, if these types of light goes to my body or somewhere sometimes it can go even in my eye, that will not damage my eye severely. Sometimes if you put your light for a long time, you can feel that you cannot see very clearly. But if you have some ultraviolet light, that means the light which has very high energy, if it comes to your eye, then your eye can be damaged or you can lose your sight. So why this UV light only, not visible, because if we see the energy of the light, UV and visible, the energy of visible light is quite low compared to the ultraviolet light, because we know the energy equation. The energy okay, let's see if I can write down, otherwise I have one there. Okay, energy energy of the wavelength or light equal 1238 1238.85 divided by lambda. 1239, this is a constant factor, and the lambda, that means wavelength. Wavelength, if you consider, yes, this 85, 1239.85. So that is the energy of the light, and this is energy, and this is the wavelength. Wavelength, that means if I consider for the UV light, the energy of UV light, the wavelength for UV light is around 100 nanometer to 360 nanometer. For visible, you will get visible, you will get, I have mentioned 400, close to 400 to 800 nanometer. So let us choose any light from here, maybe in between 600 nanometer, and from there we consider 150 nanometer. Then you can calculate the energy for the two different lights. 1239.85 divided by 600 nanometer, you will get the energy in electron volt. And for this one, you will get 1239.85 divided by 150 nanometer. That means you will get that much energy. Maybe you can calculate from using your mobile how much energy you can get. For this one, you will get around 2.1 something, is it? Approximately 2.05. Okay, fine. 2.05 electron volts, and for this one, okay, equal 8.22 electron volts. Now you can realize this is our UV light. That means the light coming from the sun, what we consider or what we call the ultraviolet light. This mass energy is very high, at least 4 times compared to this, isn't it? Exactly 4 times. What we can say 2.05 multiplied by 4, it will get 8.20. That means 4 times higher the energy of the UV light compared to the visible light what we are considering. That means if this light fall on our body, or especially for sensitive skin, sensitive means which is very skin, sometimes it can be, normally skin we do not consider sensitive, but eye, this is very sensitive to light. So if the UV light come onto your eye, then it can be damaged, and this is not enough energy to destroy your eye. So when we go outside in the sun, we should use sunglasses to protect the ultraviolet light, not to protect the visible. Because if you protect the visible, then you cannot see. you need to see. So we use the sunglass in that way that it can protect only the UV light, not the visible light. Because if we protect the visible light, then we cannot see anything. Is it? Okay. So UV visible spectroscopy is a widely used technique in many areas of science, ranging from bacterial culturing. Actually, what I have mentioned, that is not related to the UV visible spectroscopy. That is something else what we use in daily life. But UV visible spectrophotometry, this is a widely used instrumental technique that we can use this instrument to study the presence of any molecule or a sample, and also to quantify how much the sample or any molecule present in a mixture or somewhere. So this is very widely used instrument. How it works, we'll know one by one. UV visible spectroscopy is an analytical technique that measures the amount of discrete wavelengths of UV visible light that are absorbed by or transmitted through a sample in comparison to a reference or blank sample. Okay. This is my UV light, visible light, is it? Now, if I put this light through this one, maybe it is not very clear. You can see something? That means this substance is not completely absorbing all the lights. But if you can see something. But if I increase the layer, in that case, okay, right now it is very difficult to see something. Is it? You cannot see anything. But if I increase only the single layer, you can see something, some shade. Is it? Maybe you can see from this side. You can see some shade. Okay? But if I use two folds, in that case, you cannot see anything. Nothing is going through. So that is the amount of discrete wavelengths of UV or visible light that are absorbed by or transmitted. If I put two folds of this paper, then it has the capacity to absorb most of the light. But if I use single fold, it can have the capacity to absorb certain portion. You can see in the front side, you can see lot of light. That means it is reflecting many of them and transmitting very little fraction. Is it? So the amount of discrete wavelengths of UV or visible light that are absorbed, it is absorbing some of the light and transmitted very little, depending on how much thickness or what is the material inside, depending on. So transmitted through a sample in comparison to a reference or blank sample. If I consider reference, right now I have nothing here. This is completely blank. So if I consider with respect to this is my blank, and if I consider with respect to this blank, then it is absorbing or reflecting how much we can standard or we can measure. This property is influenced by the sample composition. What types of sample? If I put single folded this paper, it can transmit some of the light, but if I use this one, you cannot see anything. Is it? Because as it has very high thickness, and also the material of this substance and this substance is quite different. Therefore, we can see that the property is influenced by the sample composition. this sample or this material has high absorption, and this one has little bit less absorption, so that it can transmit some of the light. 33 is online. Okay. Light has a certain amount of energy which is inversely proportional to its wavelength. Already I have mentioned like this. This is the energy is inversely, if we consider this is a constant, that means E proportional to 1 by lambda. I should not write down this way. This is the lambda, is it? So this is constant. This term is constant. So energy of the light is inversely proportional to the wavelength. So first, shorter wavelengths of a light carry more energy, as already we have seen that 150 nanometer has 8.22 electron volt, while 600 nanometer has 2.05 electron volt. That means shorter wavelength has high energy compared to the longer wavelength. A specific amount of energy is needed to promote electrons in a substance to a higher energy state, which we can detect as the absorption. Okay. If you are familiar with the electronic configuration, let us consider sodium. You know the electronic configuration for sodium like this. First cell, 2 electrons. Here, 1, 2, 3, 4, 5, 6, 7, 8, and then plus 1. Now, if you put some energy, you are familiar how the electron configuration is being, and you are familiar with another word that electron can jump from one energy level or one orbit to another by gaining some energy, certain amount of energy, is it? So let us consider it has some energy. The center of the energy, this shell or this orbit has the minimum energy, is it? First shell will have minimum energy. So when we have this electron has some certain energy. That means in the first shell, that time if you have some energy from outside, you are giving some energy to this atom. In that case, if some of the energy is gained by the atom, then this electron can jump to either this shell, or it can go from here to here also. Possible? Because if we give some energy, normally, if we put some energy, now how will we put the energy? Or how will we get the energy? That is given by some light. So we put a molecule like this atom, and we are giving some energy to the atom to shine the atom, and if the wavelength is corresponding to, okay, I have that line. Here you can see. Here, if we put some energy, what I have shown here, that means we are giving some energy to the atom. In that case, it is gaining. This is our ground state. Atomic ground state. In that case, that means if we consider this is the first shell. Now, if the electron absorbs some energy, it has some capacity to jump from the first shell to second shell, or first shell to third shell, like this. Say here you can see this is our ground state. That means we can consider this is a bonding. So if we put some energy, it can jump from here to here, or even here to here. That can jump possible, because we have shown for this sodium, if we put some energy to this sodium atom, in that case the electron from the first shell, it can jump to the second, or from first to third, or even from second to third. That is also possible. Here you can see we have some electron consider. We have some electron here. So if we give some energy, it can jump from here to here or from here to here. Anyway, it is possible. Okay. Then for any molecule, if we give some energy, normally all the molecules try to stay in the ground state. That means minimum energy. Why we do feel better when do we sleep on a bed? Do you know? Someone can sleep on a chair, but mostly we do not feel comfortable when we sleep on a chair. We feel when we sleep on a flat surface or a good comfortable bed. That is due to minimization of energy. If you have some certain surface, you can sleep like standing like this only. That is very uneasy. That means in that case, your body cannot have the minimum energy stage. So if you have certain situation where your body is flattened so that the energy is minimum, so that you can have the energy in minimum stage and you feel comfort. Not only we, anything in the universe try to get into the minimum stage of this energy. So for any molecule, we will consider that is in ground state in the normally. But if we put some energy, depending on its capacity or its nature, it will absorb some of the light. That means some of the energy, and or it can reflect some of the light. Maybe last class we have mentioned why you can see different color of the substance. You can remember? We can see, I have mentioned that we are looking, something is red, something is black, or something different color. Can you please use laptop cursor when explaining the graphs? Okay. Yeah. Yes, that is possible. But when we use cursor, in that time, can you see my cursor? No.
Yes, Professor.
You can see those who are online, but those who are in the classroom, they cannot see my cursor. That is another difficulty. So I cannot conduct both of them together. Anyway, I will try to show you something when I use the graph or anything. So what I have mentioned here, humans are able to see a spectrum of visible light. Already I have mentioned. Just we can see from the sun we are getting a huge amount of light. Let us consider this is white light. White light, actually white light is nothing, or white, there is nothing like as white light. It is a combination of several lights. Or what about this light? Have you ever heard the light as monochromatic light? What does it mean, monochromatic? Can you see this one? Monochromatic, yes. Once again, please.
Sir, I just consider molecules are divided.
Not molecules. Monochromatic is directly related to the wavelength. So, if you have a light, I'm quite far away from you, so I'm avoiding class. Okay. So, monochromatic is directly related to the wavelength. If the wavelength of the light is single, just one, then we can consider as monochromatic light. And if you have a band, here you can see, this is the band, different color you can see. Yeah, it is not as good what I can see in my display. However, you can at least differentiate. This is yellow and this is blue and some here little bit dark. But actually, in my display, this portion is red. So I'm going to show you that UV visible. So here this side is UV and from here we are going to little bit violet and then at the end it is at 800 or red. So humans are able to see only this region, a spectrum of visible light from approximately 400 nanometers, which we can see as violet. This region actually this is violet, but as I can see, it is quite impossible to consider this is as violet. Just this is blue, and here you can see little dark blue, but not the violet. But here I can see. Maybe those who are online they can distinguish this is little bit violet. Anyway, you are familiar with the violet light and the violet color. I don't have anything we are in violet. Anyway, we don't want to violate our classrooms. Okay. So that violet and this violet are quite different. Is it? Violet color and violation. If we do not follow any rule, that is the violation. So now I hope you don't need to write down too many things because I will forward the slides to you so that you can easily find out. Yes, sure. Okay, I should share it before the class, but I could not prepare today. So hope by the end of this class or by going back to home today I will share it. Okay. Yeah. Yes, COVID sir already told me I can share you, but I'm not very familiar with the Google Classroom because in my university, what I'm teaching here, they do not use at all. So yeah, Google Drive, but I can share you immediately to the email. Maybe even. Yes, I do have all the list, and so I can copy the email address at the same time. That is not also difficult, but I think if I can use the Google Classroom, just I'm practicing little bit Google Classroom, so I need a little time to train up, and then I can use the classroom. Before that, I will share by email. Okay. Okay. So UV light has wavelength shorter than that of the visible light. Already you have mentioned. Approximately 100 nanometer. If we consider the 100 nanometer, that light has the energy around 12.39 electron volt. That means I have mentioned that the equation energy equal to 1239.85 divided by the wavelength. So if we consider this is 100 nanometer, that will give the energy 12.4 electron volt approximately. So that is even higher energy. That mass energy is enough to remove one electron from most of the molecule. If you have some organic molecule, even sometimes from water, if you have some water molecule, H2O, if you want to remove one electron from one water molecule, 12.4 electron volt is quite good enough. That means if you give that energy or that laser, actually we use laser, that is also a kind of laser, this pointer. So this is known as laser pointer. So that is a kind of laser, and we are using this laser to shine some molecule so that it can absorb and it can remove one electron, and we can get as ion of the molecule. So in my PhD and postdoc, what I did, always I used several lasers to ionize molecule. You cannot see the molecule by eye, but from instrument we could see the signal that if we do not ionize any molecule, then we cannot see any light, any signal. And if we can see some if we can shine the laser to the molecule, if it absorbs the light and it can remove one or more electrons, then it can generate some ions. We can see this is some ions. We have several things. So therefore, light can be described by its wavelength, which can be useful in UV visible spectroscopy to analyze or identify different substances by locating the specific wavelength corresponding to maximum absorbance. So if we want to confirm, in the at the beginning of this class, I have mentioned using the UV visible spectroscopy, we can qualitatively analyze. What does it mean, qualitative analysis? Which component is present in some substance? That means presence or absence. That is qualitative. And how much do you have? That is the quantity. So using this instrument, we can estimate different substances if it is present in your sample or absent, and how mass it has. So that is very important. Okay. The electromagnetic spectrum, this is your energy in kilocal. Everything are same. We are representing in different way. So here you can see the wavelengths. This is the wavelengths in meter per centimeter, nanometer, centimeter, meter, different way, and frequency. So frequency, you are familiar with the equation, energy equal n lambda, like this, is it? So we can write down E equal n lambda. That means the frequency is inversely proportional to the wavelength. Okay, so that can be represented for any laser, as I have mentioned. For this one, just you can invert 1 by the wavelength, you will get the frequency. This is another very interesting thing. When white light passes through or reflected by a colored substance, what types of color you will observe? That has some certain rule, or here you can see, oh, that is not the color what I want to show. You can see this is yellow, and then this is little dark red, but this is completely red, this region. Turn the computer. Okay, that can be one option. So you can, but can you see? Okay. So maybe I don't need to see the display here. When white light passes through or is reflected by a colored substance, a characteristic portion of the mixed wavelength is observed. The remaining light will then assume the complementary color. When we pass the white light, that means we are getting light from different sources. In that case, what will happen? What color we will observe? Just that will determine by this circle. So I have mentioned some of them. This relationship is demonstrated by the color wheel shown on the right. You can see this one. Here, complementary colors are diametrically opposite each other. That means I have mentioned some 420 to 430 nanometer. From here to here, please look at here. What is the color? 420 to 430 nanometer. Just from there to there, 420 to 430, you will see that what color you will see. Go to the opposite, 420 to 430, opposite to this, you will see the yellow. So if any material, it absorbs light in between 420 to 430, then you will see that substance as yellow. Again, The absorption 420, 430, you will get yellow, and absorption of 500 to 520, 500 to 520, this is 490, and somewhere here 500, and then somewhere here 520. So if we consider the light, that means the opposite of this ring, it should be like this one, which is red. See here, the red. So 500 to 520 nanometer light makes it red. Green, I think I have made it, this is red, is it? Yes. But here you can see black. Anyway, green is unique in that and it can be created by absorption close to 400 nanometer as well as absorption near 800 nanometer. That is very another interesting another thing. If we have this 400 or 800, any light, either 400 or 800, close to 400, 800, you will observe that is green. So go opposite to this, that should be what we can see here. This is the green, is it? What happened? That means now we can see the cursor, but I cannot see here. That is very interesting. Not, I should say this is not interesting, this is annoying. Okay, what happened? Those who are online, can you see my cursor now?
No, Professor.
You are looking there? Okay, so right now what I can do? So I need to continue in one way. So there is no way that I can continue both the system together. Even I can use some stuff. Even I cannot click here somewhere. Then how can I stop my sharing? There is no way. Again came back. Again came back in the display. Yeah. Okay. So that is done. Now the instrumentation for UV visible spectrophotometry. That is, I think you will learn in your laboratory classes. However, we are going to learn how the UV visible spectrophotometer works and what we will get from this. First thing first. So we have a light source. Here you can see this is our light source, either this side or this side, because we have mentioned that this is UV visible spectrophotometry, UV and visible. So we have a light source for UV and light source for visible. Not both the source, that means we are getting the white light, that is a combination of different lights, different wavelengths, but here we have to use separate light source because neither UV source nor the visible source can give very intense light for this instrument. So if we want to perform the analysis from 200 nanometer to 800 nanometer or 1000 nanometers, 1000 nanometer, in that case we have to use two different light sources. That means for UV region we have to use one light source, for visible region we have to use another light source, but that can be used simultaneously. This instrument is prepared in that way that when we use the instrument, we can use both the light source at the same time. Okay, so this light source, let us consider from the visible first. So from here the light is going like this way. This is a mirror, this one you can see. If this is a mirror, in that case if some light goes like this way, in that case it can reflect another way. That means if we put the light here in the mirror, you can see some light there. Can see? That means this wall is working like an, or the board is working like as a mirror. That means some of the part is reflecting over there. So if you have a light source here, if you have the light source here and this is a mirror, so you can direct the light toward this way. Just normally for any light, if you have some mirror in 45-degree angle, just if you put like this way, maybe this is 90-degree. Now rotate like this way, this is 45-degree. Now this light will go back to other way like this way. So right now what we can see, because you are familiar with the formula, the incident angle and the reflected angle will be same, is it, to the perpendicular. Okay, so this is our light source, and then we are using some mirror so that it can direct the light to this direction. Now you may have a lamp, that means it is giving different orientated light everywhere. So we have a light source, that means the light is going everywhere. So from here you are getting the reflected light by this way. Now we are using very small slit. What is slit? Glass. Gap. Yes, very small gap. Thank you. Yeah. So in this region we can have a very wide light, but if we put a very small hole or a very small gap, and rest of the lights are blocked. Just we are putting, maybe if I put how, okay, just this light is very small, so that if I use very small hole, it can see all the things. So there is no way that I can repair. Anyway, so if we put the light here, we have a very big size of light, and then we can have a very small block or a small hole, so that we can get the light, very narrow light. Is it? Because rest of the lights are blocked here. Only very small hole, so that the single light, sorry, not single, it has the light and not wide. Just certain area, maybe 1 centimeter or 0.5 centimeter like this. So we are getting light like this, whatever I have the pointer, maybe like this way. Then we have this one as grating. Are you familiar with the grating? Do you have any stapler pin? Maybe I can. Are you familiar with the grating word? Have you ever heard the grating? Okay. Can you explain a little bit? I'll show you magic. Yes. Okay. Now you can see the light this way. Just only one light. But if I put, maybe you cannot see. This is a pin. The pin from the stapler. That means I'm giving some obstacle in front of the light. Then what happens? Just try to see. Maybe I should go a little far away. Sleepy. Yeah, this is the time. This is not very good time for a class.
Like I saw it, it's like it's reflecting like a light.
It's very hard. It should be like as oh, now you can see.
Yes, it's yeah.
But it should be like that way. As I am holding one hand my pin and another hand is a pointer. It should be like this way. One side, some portion is bright, some portion dark. Bright, dark, bright, dark, like this. So this is dark, this is dark, this is dark, and other side also like this. Up to how far you have the display. It should be like this one. That means diffraction means if you have some obstacle in front of your light, it will try to bend the light and it will generate some fringe. That means some portion bright, some portion dark, some portion bright, some portion dark, like that way. But I could not show you. I'm sorry. So here, actually, what will happen? This is not a monochromatic light. That means this is not monochromatic. I have told this is a light source visible. Visible light source, that means it has different wavelength. Is it? It has different wavelength. Then if we use the grating, that will make this compound light. I said this is the compound light, the mixture of different wavelengths that can be considered as compound light. So that compound light will be divided into all its components. I can show you one figure from here. Yes. This is a white light. So that means visible light, whatever I consider. This is white light and this is a prism. Just have you ever seen the prism? Okay. So if you pass the light through the prism, then you can get all the component light will be divided from when it come out of the light, sorry, prism. That time you will get different wavelength. That means you will consider like as a rainbow. You can see the rainbow in the sky after a short rain. So that exactly happening same thing. The sun is giving the white light and we have raindrops inside the sky, and the sky is the raindrops is working like as a prism. So when lot of raindrops collect together, sun is giving the white light, and from this principle, what we are getting from the diffraction of light, that means diffraction of white light, we are getting different colors, just one by one, side by side. And then you may have the question, why we are getting one after another? Any of you have the idea? That is very simple. Simple, that means it is bending somehow. It should go like this way. If we put the white like this way, it should go like that way. Is it? It should go like this way, but it is bending somewhere. How much it will bend, that will depend on what is the wavelength. So this is the violet. It has the wavelength but minimum, then indigo, and this is the red. So it has the wavelength maximum. That means depending on the wavelength, the light which have the maximum wavelength that will bend shorter or lower or minimum, and the light which have the minimum wavelength that will bend maximum. So that depending on different wavelength, what types of wavelength are inside the white light, you will get different color one after another. And if we see several color, just band, one band, several band together, in that case we can have that several color. So we can consider that is as a rainbow. So we are using that technology in the diffraction grating, what I have mentioned here. So we have a components. What is the time? Okay. So we are using, this is the compound light, and after this diffraction grating, we can adjust the position of the grating. That is adjustable. So you can use whatever the wavelength you want to get out of this. Here you are getting the monochromatic light. That means as we have several lights, this is the grating, it is working like as a prism, and then you will get the wavelength, just single wavelength you can select. If this is another slit, is it? This is another slit. That means if we have several bands here, several bands, then just if you put a single slit here, only one wavelength will penetrate through this slit. Possible? Just we have several lights, several wavelengths, because when a compound light, that means the white light or visible light, it is coming through this slit and it is getting onto the grating, that time the light will separate into its components, all the components. In that case, you will have that these components will get like as a different band, several band. If I draw like this way, from here we get like this way. Some of them will go. So maybe one will go through the slit. Is it? Okay. So now we are getting through this slit is the monochromatic light. Now what will happen? So this is the filter and monochromatic light. That means just if we have any other light wavelength, that we can just separate out. Actually, that is enough. Only slit is enough for the separation. So we are getting only one. So we are getting monochromatic light to this. Okay. Then we have one mirror here. This mirror, again, this monochromatic light is coming here, and this mirror can reflect the light. Just if we call mirror, it can reflect 95% or more than 95% of the light. So it is reflecting the light toward this. Now this is another new word, half mirror. What is the meaning for half mirror? Half mirror. Any idea from those who are online? What is the meaning for half mirror? Anyone? Okay, that is very simple. With the name, you can easily understand that this is a mirror. It is reflecting most of the light. Maybe around, if we consider, this is reflecting 100% of the light. So half mirror means it is reflecting 50% and transmitting 50%. That is the half mirror. So if we put, so here we have some light. This is the light coming through this way, and this is our mirror. Most of the light is reflecting through this mirror, and then we are using, this is a half mirror. This half mirror will work in that way that it can penetrate half of the light. That means 50% light it will transmit through this, and 50% light will reflect by this way. So that is the function of half mirror. That means if you have some light with the intensity 100, then you will get 50% towards this and 50% towards this. Okay. Up to this, do you have any question? Okay. Now we are getting 50% light through this and 50% through this. This is the mirror, this is another mirror. We are changing the orientation of the light. When we call the mirror, then you will consider that the light is reflecting 100%. At 99.9% like this, that is also considered as 100%. So exactly similar thing, only this mirror will reflect 50% and transmit 50%. So this mirror 100%, this is 100%, this is 100%, even this is grating and this is 100%, whatever consider. So the 50% light is coming through this way, and the sample, what we want to analyze, what types of molecule or what we want to analyze, we will keep or we will take into a pot which is known as cuvette. Just like a cell, we call it like this, right? Like this, just very small 1 centimeter cell. Made of, it can be made of different types of materials depending on what types of sample you want to analyze. It can be made of plastic if it is not reacting with anything, just like as water. Then we can use glass, or even sometimes we can use quartz. Quartz is a kind of glass, high quality glass. Is it? So we can use different types of cell. Now, if we want to take the spectrum, or if we want to analyze the UV visible spectrum for a molecule, we will have to take two different cells. One exactly similar, two. Then we will put one cell here, another cell here. Just light is coming 50% through this and 50% through this, and it is going this way and it is going that way. So reflecting by this way and 50% reflecting that way. Now, if we have some mango juice or orange juice, whatever. So if we want to analyze the mango juice, if it has some protein or not, in that case, we will have that. We will put the mango juice in this cuvette into this, and rest of the things, the mango juice, we will not have the mango juice, but most of the time the mango juice made of different types of just mango and rest of the water. So we will have water in this cuvette and we will put here. That means we are putting one solvent here. That means what the solvent we have used here, we are using the same solvent in the same cell. That means we will have two cells exactly similar. From one, this we will put here, and same size, same shape, and same volume. We will put our sample here, and that would be the reference, that means the solvent. Okay. Now, if we put some, first let us consider we are keeping both the sample or both the tube just only water. Now what will happen? Any idea? Here water, here also water. What can be? Just exactly same thing. We are getting 30% light here, 50% light here. We are putting water here, water here. Nothing different. Okay. So if the water absorbs a very little amount of light, then this water also will absorb same amount of light, and we will observe the same amount of light here. That means, let us consider we had 50% here, 50% here, and the water is absorbing 1%. Then we will observe the light. This is our detector. That means something who can detect. Actually, this is not that can be considered or represented like as human eye. Human eye is very sensitive to light, very sensitive. Even till now, no instrument, no detector has been developed at the quality of our eye. And so, if we could use, but one thing, different people has different capacity, and there is no exact standard. That means if it is 50%, you will consider, oh, this can be 40%. I will say, no, this is 30%. Someone say, oh, this can be 60%. So that is a little bit difficult. So we are using some instrument having the standard number. That means what it can get. If the light intensity is somehow, that means from here we are counting 50%. So if we have both the cuvette full of same solvent or same sample, then you will have exactly the same intensity at the detector. This is detector 1 and this is detector 2. Now, if we have some sample which can absorb light, that means what I have told you, mango juice. If we put mango juice in this cuvette and water here, now you can think what can happen. Little loud. Yes. In that case, if we have the mango juice here, in that case, we will get the mango juice will absorb more light and it will transmit less light, because the water already inside has some water and inside water. So the amount of light what is absorbed by the mango juice, it will reduce the intensity. Here we should have the 50% if we do not have this mango juice here. If we have the water, maybe 1% reduce. So we should have 49% here, we should have 49% here if we do not have the mango juice. So if we have something here that can absorb the light, that will reduce the intensity of this light. That is the, if you can determine how much light you can find out here, you are getting some reference here. That means this is our reference. That means we are getting 50% out of here, 50% out of here, and we are getting, this is the reference and this is our sample, and it is reducing the light, sorry, it is absorbing the light, or we are getting, it is not absorbing at all or little bit. So how much it is absorbing? If it were the water here, it should absorb the same amount, but as it has some substance which can absorb more light, that will transmit less. That means if it do not absorb at all, it will transmit all of them. If it absorbs something, what I have shown here, it is absorbing or reflecting most of the part, and it is not transmitting at all. That means this is the, so from here we are getting the transmitted light. We are also getting the transmitted light. So the transmitted light, that means if we consider the transmitted light intensity as I naught and the transmitted light through the sample is I, in that case, by comparing this I naught and I, we can find out how much light it has absorbed. We can find out because we know this mass and this light are both the same, and we are getting, we should have exactly same. If there is no light absorbance, then this I naught and this I should be same. But as we have some sample or something to absorb the light, in that case, we should have this value little bit less. That means the transmittance is little bit low and absorbance. Now, here I have written all the things. The intensities of these light beams are then measured by electronic detectors. Here, what we have shown previously will be measured, the intensities for here and here. The intensities of these light beams are then measured by electronic detectors and compared. The intensity of the reference beam, which should have suffered little or no light absorption, is defined as I naught. What I have shown in the reference part, it should be I naught, and from the sample, it should be I. And over a short period of time, the spectrometer automatically scans all the component wavelengths in the manner described. What I have shown here, this is the light source. It is generating all the wavelengths. But this grating, you can adjust the position of the grating depending on what wavelength you want to get out of here. So just if you want to get the wavelength from 200 to 1000 nanometer, then it has programmed automatically. If you give the command to the computer, then it will automatically adjust the position so that it will generate the wavelength from 200 nanometer to 1000 nanometer, so that you can get all the wavelengths passing through this slit, and then you can get the spectrum. So the ultraviolet region scanned is normally from 200 to 400 nanometer, and visible portion is 400 to 800 nanometer. Even it can go a little bit higher if you use the sodium lamp as the light source. Now, that is the observation what we see. If the sample compound does not absorb light of a given wavelength, in that case, I and I naught should be same. We are getting I equal I naught. However, if the sample compounds absorb light, then I is less than I naught. As I have shown here, if this sample absorbs minimum amount of light, that means this I should be less than I naught, because it is not absorbing at all and it is absorbing something, so that the transmittance for this light, or that means the intensity for this light, would be little bit less compared to this. Okay, this is the graph what we plot for this. So if the sample compound absorbs light, then I is less than I naught, and this difference may be plotted on a graph versus wavelength. So how much you are giving wavelength from here, all the wavelengths, and passing the light through this way and this way. Now, if you change the wavelength for different from 200 to 800 or 200 to 1000 nanometer, then you are changing the wavelength at different time, different position. So this molecule will absorb. Here some molecule, here some molecule. Here we have some only water, and here we have some monochromatic. That is called as chromophore. Are you familiar with the word chromophore? Chromophore. Chromophore is something which can absorb the light. Okay, just chromophore is a substance which can absorb the light. So if you have a molecule which can absorb the light, you are changing the wavelength to from here, and you are passing all the wavelength through this, and depending on the property of this molecule, it will absorb some of the light and it will not absorb some of the light. So you will get something like this. We are changing the wavelength from 200 to 800 nanometer or 600 here, but we can have even longer range. So you can see, if the sample compound absorbs light, then I is less than I naught, and this difference may be plotted on a graph versus wavelength. Absorption may be presented as transmittance. Okay, absorption we can plot. Actually, what we have found here, that is the transmittance, not the absorbance, because how much it is absorbing, just we are getting a rest, not the actual absorbance. We are getting transmittance from here also, because how much light it transmits through this, we are detecting this one, and how much light transmitting through here, we are detecting this. So actually we monitor the transmittance, not the absorbance. But we can relate the absorbance and transmittance like this way. Absorption may be presented as transmittance P equal I by I naught, or absorbance A equal log I naught by I. If no absorption has occurred, transmittance would be 1 or 100%. That means when we have mentioned that if both the cuvette has water, I naught and I would be same. In that case, transmittance will be 100% or exactly the same. And if it absorbs something, in that case, we will have absorption has occurred. If no absorption has occurred, P equal 1 and absorption equal 0. No absorption. Most spectrometers display absorbance on the vertical axis. This axis is the absorbance. That means how much portion of the light has been absorbed by the sample or the molecule what we are expecting to analyze. So depending on the property for each molecule, you will have this types of peak. For one molecule, you will have a specific peak position. That means we call it lambda max. That means the position where the intensity of the sample or the absorption is maximum, that is known as lambda max. And if you know that lambda max for a certain sample, and if you analyze some unknown sample, you are getting the lambda max at this position. In that case, you can confirm the presence of that sample in the molecule. Okay, that means what we have found here. If we are taking the UV visual spectrum from 200 to 1000 nanometer, and if you get the lambda max certain, and that corresponds to the energy of that molecule, and if you can confirm this is the lambda max for that molecule, then you can confirm that your molecule contains that sample. Okay, that will be different for different molecules. So for water, that will be one. For mango juice, that will be different. For orange juice, that will even another. For gold nanoparticle, it will even another. I can remember the exact for gold nanoparticle, if the size of the nanoparticle is around 10 nanometer, then it will absorb at the 520 nanometer, because I worked on that particle so that I can remember easily. So depending on the size of the particle also, that will, so how we confirm that our particle has the size? We have taken the UV visible spectrum, and if we could find that the lambda max at 520 nanometer, then we can confirm that the size of the nanoparticle will be around 10 nanometer. And then that is our first case, that the size of the particle would be around 10 nanometer. And then we do the scanning electron microscope. Have you ever heard the name? SEM, S-E-M, scanning electron microscope, and also TEM, tunneling electron microscope. That is very expensive instruments. So we cannot see any nanoparticle, that means what are size around 10 nanometer. But if we can take the image from the SEM, SEM or TEM, then we can find out what is the size of the nanoparticle, what is the shape, not only size, also shape and pattern, everything we can see by using that types of instrument. So first we could see that in the UV visible spectrophotometer, we have found that the lambda max around 520 nanometer, and then we take the image from the SAM and TEM, and then we can confirm that our nanoparticle, gold nanoparticle size has 10 nanometer or 12 nanometer like this. So for a specific kind of molecule, you have the lambda max fixed, and that will depend on what types of component or what types of molecules are inside. So that is the qualitative analysis for this instrument. And hope in the next class we will try to understand or get idea how we can get the idea about quantitative analysis. That means how we can estimate how much orange juice, how much the molecule inside our sample has. Okay, so this is the end of today's class, and now we will take the attendance.